Okay, welcome to the solution of the problem of the day. It was posted on 7/8, and the question was derive the Laplacian as a tensor equation. And the hint was use the covariant derivative. That was pretty obvious, okay? So we can't just put the covariant derivative in here twice because that would not be a tensor equation. We wouldn't know what to do with it. So we have to use this, okay? So this is a proper tensor equation, except we don't want this contravariant derivative. We don't know what that is. And we've already learned how to replace that, right? By taking the components of the metric tensor times the covariant derivative is equal to the same thing. So the j gets absorbed, the I slides over. So we want to put that right back in there, okay? And we get this. Now, what do we want to do? We want to take the covariant derivative of this part with respect to this coordinate j. All right, now we know how to do this by now. You always take the partial derivative of whatever you're doing first. We bring our metric tensor outside with respect to the coordinate, which was j. Okay, and because this is a covariant index, it means we pick up a negative, right? The summation index always goes low to high, low to high. And we got two indexes, I, j, they go here, right? So now what do we want? Well, we want to do something with this, okay? And we've already learned that the covariant derivative of a scalar field is just the partial derivative. So we put that back in here and that back in here, and we get this expression. Okay, so this is a proper tensor equation. Now, how do we know that? If this is a tensor equation, that means it works in any coordinate system, right? So the easiest thing to do is always check something like this with the Cartesian coordinate system because it's the easiest. All right, so the metric, the tensor in Cartesian, the coordinates is what? It's the identity, the matrix. So all of the cross terms, x, y, x, z, etc., they're all zero. So we're only left with xx, yy, and zz. And there are no Christoffel symbols in the Cartesian, the coordinate, the system, remember? Because the basis vectors don't change anywhere in the space. So this whole term is gone. So we're just left with this. And what is gxx, gyy? It's just one, right? So this is the Laplacian in Cartesian coordinates, which means that this is a proper tensor equation, works in any coordinate system in any number of dimensions. All right, I'll see you later.